Imagine that the CPU is a chocolate wrapping machine. Even if the machine is very fast in wrapping, if you put the chocolates in it slowly, the overall process is going to be much slower. Similarly, in a CPU, for a CPU to process data fast, it needs to be able to access data fast. CPU speeds are generally at GigaHertz, whereas RAM speeds are much slower at megahertz. So, since RAM runs several orders of magnitude slower than the CPU will have to sit around waiting while the data is being accessed from the RAM. And so the system will still be slow despite the high speed of the CPU. This is where fast memory such as registers and cache come in. The RAM is typically a memory module that lies outside the CPU. This means data has to be transmitted to and fro the CPU along wires. The time it takes for the data to travel along the wires increases the time taken to access data from the RAM. To overcome this problem, computer engineers put a little piece of RAM right into the CPU. This is called the cache. Since cache and registers both reside inside the CPU, they are much faster for the CPU to access. There are various kinds of computer memory, register memory being the fastest. So in some of our previous videos, we saw how we used registers to store data, since accessing data directly from RAM is slower than directly accessing from the registers. But CPU register is a very small amount of data storage. Caches are a bit slower than registers, but they are larger in capacity. When the CPU wants to access a memory location from the RAM does not just transmit one single value, but instead a whole block of data gets loaded into the cache of the CPU. Let's look at a rough example of how cache works. Say you want to access the fifth date from a list of events. When you access the date of the fifth event from the RAM, the date of not only the fifth event, but the dates from 5th to some say 300th event will be loaded into the cache. So now when you want to access the 6th event or the 260th event, the CPU does not need to go to and fro to access the RAM, but can simply look up the values from the cache that is already inside the CPU. There are three levels of cache memory: L1, L2, and L3. L1 cache is the fastest but the smallest cache, making up around 2 KB to 64 KB. The level 1 cache is integrated into the CPU and operates in the same speed as of the CPU. It is further divided into two kinds: the instruction cache and the data cache. Say you have a quad-core processor, each of the cores will have a separate L1 cache. The L2 cache can be either inside or outside the CPU. They are slower than the L1 cache. The L2 cache can either be shared among the cores or can be integrated into each one of the cores. L3 cache is the slowest among the caches and is usually shared by all the cores. It can range in size from 1 to 8 MB. When the CPU needs some data, it will first check for its presence in the L1 cache. If the data is absent in the L1 cache, it will proceed to look into the L2 cache. And if the data is still absent, it will look into the L3 cache. If the data is not in the L3 cache, then the CPU will look into the RAM, then into the external memory such as hard drive, SSD, and so on. When a CPU accesses something from the main memory, that is the RAM, it generally stores it into the cache. And since memory is usually accessed sequentially, the CPU uses some clever and complex algorithms to guess as to what instructions or data it might need next. But these algorithms cannot always be perfect. Though they have an impressive 80% accuracy rate, say after the 300th event, instead of accessing the date of the 301th event, you choose to access a picture from the hard drive. In this case, as usual, the CPU searches for the data in the cache. When the data required by the CPU is not found in the cache, it's called a cache miss. When the data required by the CPU is found in either the L1 cache or in the L2 cache or in the L3 cache, it's called a cache hit. Hopefully now you have a fair understanding of how cache works. In the next video, let's see about locality.